All right, so we're going to talk about compressors. These things are pretty cool. This is a little tiny one that I have in my lab, and they get a lot bigger than this. But let's get into the theory of them and how they work and, kind of how we calculate which one of these we need depending on our application. All right, I'll put this guy down here. Now, this is a prop that I have here. I'm going to turn it on and show you a couple things. So, welcome to compressors. So, compressors are pretty cool things. And they're kind of the prime mover of a pneumatic system. So the concept of a prime mover is kind of, the engine behind the thing that makes it go, or whatever it is. So the prime mover in a car is the actual engine in itself. So the prime mover, actually we have a prime mover in a pneumatic system, and that's called the compressor. But then the compressor itself has a prime mover, which is a motor. That motor is sometimes actually a gas or a diesel engine. And sometimes most of the time you'll see it as an electric motor. So they're the prime mover for the whole system, but pneumatic systems are so cool. Like, it's just remarkable how safe they are. Let's just take a look at this. So we're looking at kind of the transmission of mechanical energy. We can do that through like pulleys, chains, cables, lots of things, shafts, turning and pushing and pulling. We can also do that through like just hoses with air in them. Or we can also do that with hoses with fluid in them, which is hydraulics, and I think you know that. But let's kind of stick to pneumatics because I think it's cooler than hydraulics. So what's going on here is we're transmitting mechanical power through putting air down hoses. It's pretty cool. And we can control these things pretty simply. When we have kind of electrical systems, it's kind of like mechanical power transmission, but to a very small degree. And that the fact is that we're actually moving electrons and they're doing things for us, and they have like a field around them, and there's this force involved. So it's kind of like the molecular physics. It's kind of like mechanical power transmission. But let's just stick to this kind of concept of air. But in an electrical system, we can control all of that stuff, like the logic. We can control things with switches and lots of other things, as you know. We can do the same thing with pneumatics. We can actually put a lot of control components in pneumatics. We can use valves as relays. We can have all kinds of different valves that we use as switches. So it's really simple. The control of mechanical power often is pretty cumbersome and big and large and stuff. So when we're actually controlling mechanical power, like in a transmission, it's a big thing, and there's a lot of gears and tension and torque and stuff. In pneumatics, all we need is valves. It's pretty cool. So the control of the mechanical power is simple in pneumatics. We just use valves. It's pretty cool. So we can also we also have these different kinds of actuators as well. So we have rotary actuators and linear actuators, and there are lots of those as well. So it's really flexible. Pneumatics is really flexible. And I think one of the coolest things about pneumatics is there's no return line. I mean, when you run wires to something, you run wires to a motor that's over there somewhere. You have to run 2 wires and a ground as well. In pneumatics, you just run one hose. The return line itself, which we'll kind of talk about a little bit today, the return line itself is the atmosphere. Because after the actuator does its thing, the air just vents into the atmosphere, and then it eventually makes it back into the pneumatic system through the breather in the compressor. It sucks that air in from the atmosphere, and then it uses it again. So the return line is just the atmosphere. It's pretty cool. And the transmission of this mechanical power, if we were to have a shaft or a pulley or a cable or a chain or something, we'd have to kind of protect it. But in pneumatics, we can just pretty much run a hose and just like use tie straps and strap it down to something. I mean, really, we're not going to be doing that. We're actually, if we have to transmit it across a factory or something, we'll actually put it in steel lines or copper lines, and we'll secure them. But it is very flexible. For instance, this hose here. I mean, I can put a lot of power, mechanical power, through this hose, and it's just a hose. Yeah, and if this actually breaks, if it gets a cut in it, it's just air. It's not going to hurt anybody. So hydraulic fluid, as you know, is going to make a mess. And electrical, if there's a break in a wire, it's pretty dangerous. You can't mess around with it. And mechanical system, if there's some kind of chain or something that's going on and the housing breaks, well, that's dangerous as well. Things can get stuck in there. Pneumatics is really very safe, and it's so friendly. And there are no shocks in the system. Like this hose, actually, if there was a lot of pressure and a lot of kind of if the system was coming on and off and on and off and off, you might see the hose kind of move a little bit. So you'll kind of watch that. Sometimes the hose will move a little bit because it has internal pressures which create force. But there's not a lot of shocks. There's not a lot of movements going on. In mechanical systems, you have a lot of like backlash, like smack, smack, smack. Things are moving around, and it can be used underwater. Yeah, pneumatic systems can be used underwater. I remember up on the lake we were fixing the dock, and I have a drill actually that's a pneumatic drill, and I had to drill some holes into the crib under the water, and I just brought the compressor and I ran that, and we had this hose that was actually a little longer than this, and the compressor was on the shore. I didn't want to put the compressor on the dock because, you know, it runs on electricity, so I didn't want anything to do with that. But I just ran this long hose out, which was cool. The mechanical transmission of the power from the prime mover that was on the shore was going all the way down the dock, and then I had this air gun and I was just using it underwater. I made sure I oiled it and flushed it out, flushed any water out of it, but yeah, nice and safe. So pneumatics, it's pretty special. It's pretty cool stuff. So what goes on with compressors is that it takes air in and then it blows air out. The nature of the air coming in is just the atmospheric air. It's not under pressure. I mean, it's not under anything more than 14.7 psi, but it's just standard air that's just here. It's atmospheric air. And then what it does is it compresses it and lowers the volume of it and then shoots it out of the compressor. So kind of think a little bit about the flow rates that's going in here. So the gas that comes in is like this, the inhaled gas. And then the exhaled gas, it is a smaller volume. But the amount of air going out is kind of the same as the amount of air coming in. So if I had this much air coming in, well, it would be compressed to this, but the same amount of molecules would be going out. But the flow rate of air going in is actually different to the flow rate of air going out. It's because we study flow rate in not how many molecules are going in and out, but what the volume of that air is. So essentially it comes in at atmospheric pressure, low, and it leaves at a high pressure, and it comes at a larger volume, and it leaves at a smaller volume. There are two kinds of compressors. One is dynamic, and the other is displacement. Dynamic compressors generally have a higher flow and a lower pressure. Dynamic compressors don't have really high flows, but they can have really high pressures. So they work under different principles, and let's kind of take a look at this, what's going on here. So the dynamic type, what it does is actually just adds kinetic energy to the air. It just speeds the air up. And as we know, we kind of talked a little bit about that last week, where we were talking about the kind of the dynamic of the gases that are inside a chamber. And, you know, the faster they're going, they create actually more pressure. And you feel that on the outside of the wall. We talked about how Blaise Pascal had an understanding of that. How the pressure that's actually felt has to do with the kinetic molecular energy that's banging up against the walls. So if we were to just increase the kinetic molecular energy, then we're increasing the pressure. And we can actually have really high flow rates with these things. And you'll see, I've got some pictures here and some examples, and you'll see that going on. So what's going on here is the displacement type actually grabs onto Boyle's law. It just says, okay, Boyle, let's make your law work. And what it does is it takes a certain amount of gas, and it doesn't add kinetic energy to it. It just goes, and it crushes it. So it kind of increases the displacement, it increases the density of the kinetic energy, kind of like that, which is, you know, increasing the pressure. So it lowers the volume, and then in that way, it actually increases the pressure. And we know Boyle said that. Let's actually take a look at what Boyle did over here. So as you can see, the pressure and the volume are inversely proportional. So when the volume goes down, the pressure goes up, and vice versa. So that's how compressors work. The displacement type of a compressor, that's how that works. So essentially, when we look at these two types, we look at dynamic and displacement, and we can see that there are a whole bunch of different kinds of these. So we're going to kind of only look at displacement. We're going to take a quick look at dynamic, but you in the pneumatics industry will most likely, if you go into any kind of industry that uses pneumatics, which is pretty much every kind of manufacturing industry. You'll have to understand the different compressors. Mostly they're going to be using displacement. There are some special things that use dynamic, and we'll take a look at those in a minute. But essentially, for the displacement, there are two kinds. One is rotary and the other is reciprocating. So rotary is actually this thing that turns, and the nature of how it's turning kind of compresses the gas. It's pretty cool. And then the actual reciprocating is just a piston going up and down, or a diaphragm going up and down as well. So, and these two dynamics, we'll take a look at this. There's the radial and axial, but essentially they're just mechanisms that are fans that are just speeding up the air. We'll take a look at the dynamic type. And we've got the radial and the axial. So the radial, or the centrifugal type, what it does is it actually takes air in the side, and this is actually creating a vacuum. So the air is actually getting sucked in here, and these fins rotate quickly. They're actually, this thing's going. It's like whipping. It's going around. So the air comes in here, and it gets displaced out here at a much higher velocity. So it's taking it in and just kicking it out at a higher velocity. And it increases, it actually compresses it to some degree. So there is a little bit of Boyle's law going on here. It compresses it to some degree, but mostly it's just speeding it up. It's actually creating the pressure from the kinetic energy itself. So that's what's going on here. And this is a good example, air mattresses and HVAC blowers. So essentially what's going on is that, those vents in your home that are, the air is coming out of there, well, that air is actually under pressure. It's actually, so the pump that's actually the prime mover in that system, the actual pump that's moving the air, well, it's a radial type, and it's sucking air in and then it pushes it out. I don't know if you've ever seen one of those fans, but they look pretty cool. They're actually just a huge one of these things. It's just much bigger than this. And you've probably blown an air mattress up. If you haven't, air mattress pumps are pretty cool. And they make a lot of noise. You can hear them going really quickly. They're a little annoying, but those are the kind you plug in your cigarette lighter or your power plug in your car, and then they go. So yeah, those are what's going on there. That's what's going on with the radial type or the centrifugal type. Again, it's just speeding the air up, but it's taking the air in one direction and then it's coming out the other. Now axial is a little bit different, and axial actually can create even a higher flow rate. I don't know about the pressures, if they're any more or less. But I know that these can create a really high flow rate. And you can see this one's actually huge. This is like a multi-stage compressor. So there's something going on here. There's a lot of air being compressed here. So what's going on here is that the air just comes in and it goes right out. And as you can see here, wind tunnels and jet engines work under this principle. Yeah, so there's a lot more air flowing through these things. It's pretty cool. So the air just comes in one side and it comes out the other. But as you can see right here, what's going on is the air is actually getting compressed. So the same amount of air is coming in here, and it's getting compressed, and it's being pushed out here. So Boyle's law is actually happening here, but more the fact that the pressure is created because we're speeding up the air. So as far as displacement goes, or reciprocating goes, it's actually changing the volume of the air. It's taking air in, it's decreasing its volume, and it's sticking it out. And that, again, that's the most common type that you'll probably be dealing with in your future. So all the piston types, we use it for manufacturing, automotive, automation, and construction, and painting, and home use, recreational. I mean, if you have a little compressor that you want to fill up your tire for your bicycle or your car, I mean, you've heard those things. You plug those they're 12-volt things. You plug them in your power port in your car, and but you can hear them vibrating, and you can kind of hear the speed at which they're going. You can hear their frequency. If you put if you plug in one of those pumps for an air mattress, you can hear they're a lot faster. They really work on speeding up the air. These are actually just compressing the air by actually changing the volume. So yeah, and they can go up to like 4,500 psig or even more. You can get these things that compress even more. I mean, the ones that go really up into the thousands, they're really specialized, and we'll talk about why they need to be specialized in a minute. And that's what's actually going on. So we take a look at this. So it's inhaling gas, it's compressing gas, and then it exhales gas. There's another kind of type here that's also the reciprocating type, but it's actually using like a diaphragm as opposed to a piston. Let's take a look at this. So there's metal scraping against metal. We don't want to put precious gases in here. I mean, we're actually going to be adding things. For instance, what's going on here is that there's actually grease and oil in here, right? So there's oil in here. There's a little bit of oil that gets into the gas. Let's say we really had this precious gas, like we were dealing with a noble gas or some other kind of gas for a scientific purpose. We don't want to disturb it. We don't want to add anything into that gas. Well, there's going to be a problem. We're putting particulates, we're putting iron filings and particulates in there, and we're putting gas in here. So for like industrial applications like manufacturing, automotive, and running pneumatic cylinders and stuff like that, it's okay. We can put filters on this and we can deal with it. But if it's a precious gas, or if it's a gas that can explode, yeah, we don't want to do that. So we're going to actually compress it just with the diaphragm. So the diaphragm is going up and down and up and down. It's compressing it. So the food industry uses that because, they don't want oil in whatever the food, whatever the actuators are that dealing with the food, or maybe even for just actually blowing air around near the food. We compress the air. We need to actually have like, even in this situation here, if I were just to like be blowing air near my food, I'd want to make sure that that air didn't come from like a regular compressor with a piston in it, because there are a lot of contaminants that happen in there. So yeah, scientific, chemical, and toxic and combustible gases, we have to make sure that they don't blow up. So we're going to use these guys. They're pretty cool. In the medical industry, most certainly all of these, all of the pumps and stuff that they use are like that. In surgical procedures, or compressing oxygen, for sure. They have to use these for compressing oxygen because the oxygen can blow up real good. So as far as the two kinds of types, what I want to do now is I kind of want to jump into a little bit of the gas law theory. We have to understand the gas laws to kind of move forward here. So really, if you didn't get that, like go back to last week and watch that video about the gas laws, because you have to understand that to move forward at this point. So what's going on here is that, Charles and Gay-Lussac, they actually looked at temperature. They said, what's going to happen to the pressure and the volume if we change the temperature? Boyle was just stuck on, hey, I'm sticking with temperature. I'm sticking with pressure and volume. So these other dudes, they looked at this kind of how temperature is going on, and that's what we're going to do right now. We're going to discuss temperature. There are kinds of two ways to compress the gas. When we compress the gas, as you understood and as you learned last week, that the temperature increases. Now the amount of energy in the system stays the same, but because we're compressing it, the density of the energy is greater, so therefore the temperature went up. So the temperature goes up, and there are kind of two ways to compress gas. And as we make that volume decrease, we know the temperature goes up. Okay, well, also the pressure goes up. So when I decrease the volume, the temperature and the pressure go up. So it's actually more energy to compress gas if we leave the heat in it. If we don't allow the heat to leave, it's actually it's extra work to compress it. So, but what happens if we don't let the heat leave? Well, the pressure actually goes up higher, because I know that the higher the temperature, the greater the pressure. So if I were to compress gas and let the heat leave, actually, if I were to actually suck a lot of heat out, even though I were compressing the gas, the pressure would stay the same if I could take enough heat out. What we do is, there's kind of two ways of compressing gas. One is, we actually compress it and we don't let any heat out. We call that adiabatic compression. The other is where we compress it and we let enough heat out so that the heat of the gas is the same. And that's isotonic. Sorry, that's isothermal. Isotonic is a word that's used in the kinesiology, but we won't get into that. So isothermal is what's happening is that as I'm compressing that gas, I'm letting the heat dissipate to the point where it stays the same. The temperature stays the same. So I'm letting the heat dissipate and the temperature stays the same. So that is isothermal compression. And that's really what we want for most of compression. Adiabatic is pretty cool. What happens with adiabatic is that we leave that heat in there and the pressure actually increases a lot. And the temperature increases a lot. Like it really heats up to the point where we can actually ignite fuel. Yeah, and that's how diesels work. So diesels are pretty cool. So a diesel engine utilizes the properties of adiabatic compression, and what's happening is that the heat is not allowed to escape. So as we compress that gas, like a lot, like it's compressed like 10 or 12 or 13 or 14 times, so the volume is decreased by that much. So the temperature goes up by that much. And we know that, when we're looking at the temperature, if I were to double the temperature and the temperature was like, say, 20 degrees Celsius. If I were to double it, it doesn't go to 40. It goes into the hundreds, the 300 or the 400s of degrees. So it gets really, really hot. It gets so hot that it actually ignites. And that's pretty cool. So that's why you don't actually have, I don't know if you know this or not, but diesel engines don't have spark plugs. Yeah, they just compress it so much, it gets so hot that it just goes, it just blows up. It doesn't actually blow up, it combusts, but it's fun to say blow up. Okay, so here we go. So isothermal compression. What's happening there is that as we compress it, we let the heat vent. We don't want the heat in there. Actually, you know, it's better to let the heat out because then we have to spend less energy compressing it. So what's happening here is that we have something called a multi-stage compressor. So now not all compressors are multi-stage, but they'll all have fins on them. They'll all have an ability to displace that heat. They don't want that heat in there. It's actually inefficient for the process. We would rather take all the heat out, actually as much heat as we can out, and that allows the compression to happen with less energy. So it takes an enormous amount of energy to compress it. The other thing is that, you know, once we actually compress that gas, what's going on is that, let me show you this compressor here. If I were to not let any of the energy out of here, let's take a look at this. So if I didn't let any of the heat energy, the air in this tank would be really hot. And I don't want hot air in my tank because essentially this thing is just sitting around in the atmosphere, just here. It's going to cool down. Okay, so if I had a certain amount of compressed air in here that was really hot, I didn't let any out, I was totally adiabatic, and this was really hot air in here, well, the problem would be that that heat would eventually dissipate, and we know that when we dissipate the heat from compressed gas, the actual compression of the gas changes, yeah, and my pressure decreases. So it's not good. So if I were to have adiabatic compression and leave all that hot air in the tank, it would cool down and the pressure would decrease. And that's no good because then I gotta compress it again. Well, if I were to compress it again and put more air in, and then that hot air would decrease and vent again, then it would lower the pressure, and I would do it again and again and again until I actually had 100 psi in there. Because every time I compressed it to 100 psi, it would cool down. It would go down to like 50, and I'd compress it again, and it would cool down. Eventually, I would be able to get it up to 100 psi, because I'm letting the heat dissipate slowly in this canister that's just kind of, you know, hanging out in the air. Well, why don't I put fins somewhere, and let the heat dispense even before I put it into the tank? So compressors will have fins on them to dissipate that heat. And we also have a double stage compressor like this. It's pretty cool. So, and actually you can see Gay-Lussac's law in action here. We'll study that in a second, but let's just take a look at this. The air is coming in here, it's getting compressed, and then, you know, the temperature increases because the density of the heat, the thermal heat, is actually less, or is greater. The density is less because of less volume. The density is more because there's less volume. Okay, so let's go on. What's happening here is that this air is coming out of here and it's going through this intercooler. Now, when this air goes through the intercooler, the compressed air through the intercooler, it's hot, but it dispenses the heat out. So it radiates the heat out, and also there's air going past here that's pulling the heat out of that. So it cools down. When it cools down, its volume changes. Because if we have compressed gas, or if we have any gas, and we cool it down, its volume changes. So let's just actually take a look at this and see why the temperature goes up. So what's happening is that my initial pressure, P1, is atmospheric pressure, and I'm increasing the pressure, and then that would be my P2. And my P2, as we know, is going to be larger than my P1 because I'm compressing it. And I'm dealing with the temperature with T1, and I multiply that by a number that's greater than 1, and well, my temperature is greater. So temperature's going to go up. Temperature's going to go up. So we want that temperature to go out of here. Now watch this. This chamber and this chamber are different sizes. What's up with that? Well, let's jump into the whole concept of this Charles law, this one here. Let's take a look at the volume. So I know that I've got a certain volume coming in, I'm compressing it, and the volume is changing. It's getting smaller, but the temperature goes up. Okay, so when my temperature goes up, okay, so what's going to happen here? Well, my temperature goes up, but so my T1 is high, but I'm venting it through this intercooler. So now my T2 is lower. So in this case, this number is lower than this number because I'm venting the heat. Okay, so, well, if I take my initial volume and I multiply it by a number less than 1, then my final volume is smaller. So the volume of the gas decreases by the time it comes out here. Now, we're saying that the pressure is staying the same. So the pressure in here is increased, absolutely. So what's the temperature? The temperature is left to vent. If we let the temperature vent and we want to keep the same pressure, then we're dealing with a smaller volume. So we have the secondary piston smaller. See what I tell you? You have to understand the gas laws to really wrap your head around how a compressor works. So what I want to do now is actually run my compressor for you. And we'll talk a little bit about the components and actually what's going on here. But so one thing is really cool is that, so there's an automatic control system in here. Let's just take a look at this guy. So what I'm going to do is I'm actually going to let a little bit of air out here, and then we'll see this thing comes on automatically. So there's some kind of control device in here. It's actually just a pressure switch. It's pretty simple. Actually, I'll show you this pressure. Whoa, whoa, stop that. Oh, good. I got hose whip. I want that to, okay, this thing should, come on. There, come on. Okay. So that quick disconnect, we'll let this thing go. See, now, in here is the pressure switch. Just give it a sec, it'll come up. Listen to it when it stops, it'll go. Did you hear that? Huh? So that is actually, I'm going to do this. That's hose whip. So what's happening there is that the piston itself, when it's done, the compression stage, oh my, the piston head itself, the top of the piston, this area here, right in there, when the piston stops, it still has compressed gas in it. I mean, that gas has gone into the tank. There's actually a check valve that doesn't allow the pressure from the tank back into the piston, but still, the line from this chamber here to the actual check valve still has compressed air in it. And what's happening is that when that piston tries to kind of move and come up again, it's dealing with compressed air, and it doesn't like that extra pressure, and it's hard on the compressor. So what we do is, when this thing is done and the air's gone into the tank, we actually just, we have this little vent that vents the pressure out of the top of the head of the piston in here, and then that allows that air pressure to go out. So when the compressor starts again, it doesn't have to start up and fight that high pressure. So that's what that little psst is all about. So let's take a look at here. So we know the intercooler does this. We know the volume goes down, and that's cool. The pressure's actually going to stay the same in here, and then we compress it again. So it's a two-stage compression. Pretty cool. We also have multi-stage compressors where not only you have two of these, but you have three of these. And sometimes we have aftercoolers where we really cool the air down a lot. And sometimes these intercoolers are actually more than just a fan blowing air. By the way, there's a fan here. More than just a fan blowing air over your intercooler. You'll actually have some kind of like liquid cooling or some other kind of cooling that actually works on like a air conditioner type of system. And sometimes when we do that, we're compressing the air like a lot. We're really kicking it up. Like scuba divers, those tanks, those are like 3,000 psi. So, and they have special multi-stage compressors that have really efficient cooling in them. So that's what's going on there. So let's just take a look at some of the components here. And I think a lot of these things make sense. So this is the actual air that comes out of the tank. Now there's actually a check valve in here, and then there's that little vent valve. We don't see that in here. The general kind of gist of what's going on is that the air comes out of the compression, and you can see these fins here, so that are actually taking the heat away. So this goes into the tank, and then we have a tank, which is really important that we have to actually put the air somewhere. We got to make sure that the air goes somewhere. We store it in there. So, and then this is our prime mover. The motor is the prime mover. So again, this whole compressor is the prime mover for some kind of mechanical, some kind of pneumatic system. And the prime mover in the compressor is the electric motor. So the prime mover is here now. yeah, the power goes in here, and then the compressor and the piston goes here and all that. So this guy too is the air intake. So the air comes in here. So the air going in here, or we call this the breather. The air that comes in here gets compressed, and then it gets compressed and it goes out here. So number 6 is the control switch. So what's going on there is actually it's a pressure switch. And it's just this little plunger that moves up and down at a certain pressure, and there's a spring pushing it down. You can actually adjust it. So you can adjust the counter force of that spring. So when the pressure is enough, it pushes on that spring and it physically moves a little pin up and down, which moves contacts, and it just becomes open. So the switch becomes open. So normally it's closed, but if you pressurize it enough, it becomes open and just turns the pump off. Okay, so yeah, the control switch, the relief valve. Relief valves are really important. Actually, let's check out the relief valve on this guy. So relief valves are super important. Let's do this. Oh! Sorry, let me redo that. Can I get this thing stuck on mine? Okay, there. So, yeah, relief valves are really important. What happens is if the compressor, we'll let that thing stop. So if the compressor actually gets, if it, like, for whatever, the control switch doesn't work, it's just going to keep going and going and going and going and going. And eventually something's just going to blow up. Something's going to break. So the relief valve will say, okay, something's going on with the system. It's like a backup safety thing. So also the relief valve will go, if the temperature in that tank goes up to a really high degree for some strange reason, then the pressure will go up. And then the relief valve will let that extra high pressure out. So the pressure gauge is important as well. We have to know what the pressure is. And, you know, that makes a lot of sense there. That's the pressure gauge. The manifold is actually just, you know, the manifold is, you've seen the manifolds in the pneumatic board. They're just, you know, a manifold is the concept where it's an open cavity and there are a bunch of connections to it. The regulator is important. So the regulator is that thing here that allows me to adjust the pressure, right? So these guys are the regulators. So actually, let me just turn that guy. I'll crank that up. You can see it moving, and then I'll crank it down. That's the regulator. What the regulator is doing is it's regulating not the pressure in the tank, but it's regulating the pressure that's coming out of that hose. It's kind of important that we kind of pause on this for a second. The regulator actually will affect the flow rate to a small degree. So what's happening is that the air pressure that's coming out of the tank, it's like a voltage dial. It's like a variable voltage power DC power supply. So we can actually just turn the dial and the voltage coming out changes. In this case, the pressure coming out changes. And we know that, you know, if I were to change the voltage, the current would change as well, wouldn't it? Yeah. So in this case as well, the flow rate changes as I change the pressure. We'll talk about that more when we look at some really cool examples about how to actually kind of rate these and how to design a system. Well, once we've designed a system, how to rate a compressor. So we know that we've got a certain amount of flow rate required at a certain pressure. So which compressor do we need to get? Yeah, so we'll go into that. So supply line, okay, that's cool. So what's going on is that's just the air coming out. So the receiver tank and the water drain, let's just kind of pause on this for a second. We won't get into actually how to rate these things, but you can actually design your own compressor and actually build your own tank. So design the size of the tank. Now you can look into that further if you want. There are formulas and stuff for that. But generally you're going to buy a compressor that's already there with its own tank on it. And it'll just have a label on it that tells you how much flow rate it can give you at whatever the pressure is. And that'll actually be dependent on the tank. So the other thing is that this drain valve here, now you guys know this, but air has water in it. It's got a lot of water in it. When we compress air, that water is also compressed. So if I were to take all the air in this room and compress it into a cup this big, it would have a lot. There's actually water in here. It would have a lot of water in it, right? I just made a mess on the floor. So, but there's water in it. I mean, that much water is actually probably in this whole room. So if I were to compress all the air in this room, I'd have that much water that I just poured out of that glass. And that water itself now is stuck in my tank. What am I going to do? Well, you have to vent it out. So this water drain is actually really important. You can get automatic water drains, as you guys know. But what you need to do is you need to drain yours often. It depends on where you're using. If you're in Arizona, then it's probably not going to have to drain very much because not a lot of water in the air. But if you're in a moist climate, there's going to be more and more water in there. Or if you're inside some kind of facility that actually has moist air. So you have to make sure you drain that. And when you drain it, actually, it's pretty cool. The drain is clockwise. You turn it clockwise, and that makes it open. So the water will come out. It'll be a little bit dirty too. So put something underneath it to capture it, because a lot of water will come out. So you have to drain that. You have to make sure you drain that. Cool. So we just talked about all of these things. You guys can go back on all these things when you go to the test, because I'll ask you about them. And you'll be like, oh, I better open the PowerPoint. Okay. So what we're going to do is talk about inlet air and outlet air and why they're different. And then I'm going to do another video on a bunch of examples where we actually put some math into this. We use the gas laws to be able to calculate what compressor we need. But right now, let's talk about inlet air and outlet air and why pressure matters. Like why the pressure of the air coming in and the pressure of the air going out actually change the flow rate. What's up with that? Okay, so we've got this picture here. Essentially what's going on here is we've got a nice little air filter in here. That's the breather. So the breather is the air coming in. So the inlet air comes in here and then the outlet air comes out here. Now, I put a pressure regulator in here for a very important purpose. The fact is, depending on what this thing is set to, the outlet air changes. Okay, so let's take a look at this. I've got these 3 different ways of looking at the air coming in, and they're all just the air. They're just this. Okay, so that air goes in, and then the air going out is at CFM. We've calculated CFM. We know all about CFM. When we're doing calculations for CFM, we're dealing with compressed air. When we're looking at SCFM, ACFM, or ICFF, we're looking at just this, just normal air that's coming in. So we'll study those different ones. So essentially it's cubic feet per minute. We know that one, but that's only when we're talking about compressed air. So the standard cubic feet per minute is essentially, you know, this STP, this what's going on here, this air here, and it has a particular value to it. So it's 14.7 psi A, and it's 86 degrees Fahrenheit or 20 degrees Celsius at 36% humidity. Now there are some different people that take a look at what STP is, and people debate whether it's this or that, but it's around those numbers. But that's generally just this air. Okay, so what's going on is that we get inlet cubic feet per minute and actual cubic feet per minute. That's actually just like saying, well, it doesn't really matter how much moisture is in the air. It doesn't really matter what the pressure of the air is, whether it's 14.4 or 14.8 or 14.7, or maybe even if we're up on an airplane where it's like 8.7. So if we're in an airplane, we're way up in the air, and the atmospheric pressure is 8.7 psi A. So that air coming in, well, it's no longer SCFM. So we're not going to study our compressor in SCFM. We're going to actually study it in ICFM or ACFM, either one. So what's going on there is that I kind of like to just describe the inlet flow. So I kind of like to say ICFM is just this inlet flow, whatever the air is that's coming in. So it doesn't really matter what we call these things. Often compressors are rated in just CFM. But sometimes they're rated in SCFM, and sometimes they're rated in these as well. So if you ever see these, just look them up and just essentially just remember it's just the air that's coming in. Whether it's standard temperature or pressure up a mountain or pressure down a deep hole in the earth and the air pressure is a little higher, it doesn't matter. It's the air going into the compressor. All right, let's talk about inlet flow and outlet flow. So essentially they're different things. We just have to put names to them. We just say inlet flow and outlet flow. And the reason they're different is because the volume changes. The amount of air coming in is the same as the amount of air going out. It's just the volume is different. And we actually we study the flow rate in volume per unit time. But we're not looking at the amount of air per unit time, because again, the amount of air is the same. So when we take a look at this, we're having 2 different flow rates. The flow rate in and the flow rate out are actually different. Even though it's the same amount of air, it's different because we study flow rate in just volume. Okay, so that's cool. So we've got this inlet flow and outlet flow, and we know that we measure them in these different things. This is inlet flow, this is outlet flow. CFM is cubic feet per minute. It's only when we talk about compressed air. All of these are the inlet flow. Okay, so we've got our inlet flow and our outlet flow. The wrong way. So, but which one do we use when we rate a compressor? Let's say I wanted to go buy a compressor. Would I go and buy it and say, hey, you know what? I want a compressor that has this much inlet flow. Or would I say, I want a compressor that has this much outlet flow? Well, the thing is, we'll learn actually that the outlet flow is dependent on the pressure that we set it to. That regulator, that dial that we actually turn, when we turn that to a different pressure, well, the outlet flow actually changes. So wait a second. If I've got my inlet flow and my outlet flow. And my outlet flow changes depending on what I set the pressure to. Does the inlet flow change as well depending on what I set my pressure to? Actually, yeah. So how do I rate a compressor? What do I just say I want a high flow rate or a low flow rate? What do I do? Well, the rating of a compressor is dependent on the pressure setting that you set it to. And we can actually get compressors that are rated for inlet flow. Most of them are rated for outlet flow. So let's take a look at this. So what we've got here is most manufacturers rate their compressor for the outlet flow. And actually they have to rate it with the pressure. They have to say, well, if you're going to run it at this pressure, then it will have this outlet flow. If you're going to run it at that pressure, then it will have a different outlet flow. The inlet flow also is dependent on the pressure to some degree, but essentially what's going on is that you won't see these as much, but you will see compressors rated in these. But they also, when you see them rated in these, they don't actually give you the pressure. They're not dependent on pressure, although they are, but not as much. Let's just stick to this, the CFM, at a particular pressure and look at some examples. So what's going on here? In the end, all the user wants to know is, can they run their system? All of the actuators or whatever it is, all of their tools or their operation. So what's going on is that all of those tools in that operation is set to a specific pressure. Okay, so if it's set to a specific pressure, well then what's the flow rate at that pressure? Well, you have to calculate that. You have to actually go and calculate all your actuators, and you have to say, well, they're running at a certain PSI and they're moving a certain amount, and the displacement is the CFM, the cubic feet per minute. We know the displacement per unit time is going to be ending up, you're going to calculate it as CFM. So now we've got this. We know the CFM and we know the pressure. So let's move on and we say this, okay, so I'm going to rate my compressor on this because most compressors are rated on this. So let's just move on here. So we know that the compressor here comes with these ratings. Let's take a look at this. So it says here that if you run it at 90 psi, if you go and buy this DeWalt job compressor, what I'm saying is job compressors, you'll see this on construction sites and stuff. So if you go and buy this and you run your tools at 90 psi, they will have this compressor can give you a flow rate of 4 cubic feet per minute if you run it at 90 psi. So if you run it at different pressure, that flow rate will be different, and we'll see whether it goes up or down or whatever. We'll see that. So if you take a look at this guy, there are actually 2 ratings on here. At 40 psi, this thing will give you, if you run it at 40 psi, this compressor can give you 11.8 cubic feet per minute. No problem. That's what it's designed to do at 40 psi. Watch this. If you run it at 90 psi, now you're only getting a flow rate of 10.3. The reason is when we compress air greater, the volume goes down. When we compress it to 90 psi, the volume has gone down. Okay, so if my volume has gone down, well, then my flow rate's going to be less. Absolutely. So it all depends on the pressure that this air is coming out, and then the flow rate changes. Again, just like voltage. If you go to your variable DC power supply and you change the voltage, the flow rate will change. Absolutely. So they're very dependent on each other. So let's talk about the flow rate of air, the pressure of the air, and the volume, and how they're all linked. So we're going to start with an example. But we're talking about everything in absolute pressure. And the reason we're talking about everything in absolute pressure is because we have to look at these ratios that we're studying in the gas laws, and we know that we can't use gauge pressure in the gas laws. So moving forward, we have an example here where we've got a pressure of absolute pressure of 50 psi. Let's say we're looking at a multi-stage compressor. So in the first stage, the air coming out of the first stage is at 50 psi A, and the flow rate of that air coming out is 10 cubic feet per minute. Okay, so now that flow rate is going to go into the second stage, and it's going to be compressed. So the volume is decreased by half. Okay, if the volume is decreased by half, then what's happening is that the pressure is doubled. If the volume is decreased by half, the pressure is doubled. So the pressure goes up to 100 psi. Now that is if it's an isothermal reaction. Again, all of these things that we're studying are isothermal. We're going to do all our maths with isothermal unless we were doing adiabatic compression. Then we would have to put the temperature in. But right now we're not worrying about the temperature. Okay, so is the flow rate going to be the same? Is the flow rate going into that compressor? So if the flow rate actually, let's say the flow rate coming out of the first stage is 10. The flow rate coming out of the second stage, is it going to be 10? Well, no. It's going to be half. It's going to be half because the flow rate at 50, so the answer is no. There will be half the flow rate that it was at 50 psi. We know that because we've just changed the volume. So let's move on here because I think you get that. You understand that. So if we actually wanted to kind of take the general gas law and throw all of these things into kind of a formula that we can use to study how flow rate and pressure and volume are all linked, then actually we take the general gas law and we throw a T in it because this is great. I love throwing like T into one side of a formula and the other side, and all of a sudden you get rates. It's pretty cool. So we can actually take the general gas law and just kind of move it around a little bit. So the general gas law, if we were kind of manipulate it all, change it around, we can say it's so it's P1 times V1 times T2 equals P2 times V2 times T1. So all of a sudden, and that capital T is for temperature, we know that. All of a sudden we divide both sides by T because we can do that, because the time in and the time out are the same, because it's just time. So all of a sudden, if we throw a T in there, oh yeah, look at that. We've got our volume over our time, and we get a flow rate. So let's manipulate this a little bit more and get rid of that VT and just call it a Q. Okay, so this is the derivation of all of this, and again, if we were talking about adiabatic compression, we would need to use this guy to study how the flow rate, how the pressure, and the temperature, and the volume are all linked into each other. So we'd have to use this. But because of volume and time, we know the flow rate is going to be different on one side and the flow rate is going to be different on the other, and we know the time's the same. So as opposed to just studying the volumes, we're going to study the flow rates because, you know what, we're after flow rates. Flow rates are actually really important for us because that's how we rate compressors. So this is our general form here that we're going to use when we're dealing with isothermal reactions. Again, if we're doing adiabatic compression, we're going to use this one. Isothermal, we're using this guy. So let's use this formula and actually use it to select a compressor. Get the right compressor for our application. So here we go. This is a compressor selection. So I'm going to leave you guys at this. I'm just going to pause on this, and I'm going to say you can go and watch this next video on these examples of how to actually apply the rules and the regulations and the formulas that we just learned. So let me know if you have any questions.